Okay. So today we're going to talk about fibrations. So, I'll review what, we'll review why we care about fibrations from the perspective of like free abelian groups and Dole-Thom theorems. And then we'll, a fibration is a generalization of a fiber bundle, which is a generalization of covering space. So we'll review what those are. Then we'll talk about lifting properties for covering spaces and fibration or fiber bundles, and that will give us the definition of a fibration. And then we'll talk about the long exact sequence of homotopy groups, and then we'll talk about applications. I have like a fear that there's slightly too much material today. Yeah, but still interrupt me. I'm happy to bore Manuel for the first 15 minutes of Tuesday's class if I don't finish everything. Okay. So yeah, so our goal is to show that this is a typo. Is it yellow? The x. Okay, yeah. To show that the map from z of x to mod z of y is a fibration when y is a sub CW complex of x. So that's the goal for next Tuesday. So the goal for today is to learn what a fibration is. Some people maybe know what a fibration is already. Yeah. Okay. Oh yeah, and I guess the reason why we want this map to be a fibration is then it'll give us a long exact sequence of homotopy groups, and this will correspond to the long exact sequence of a pair in homology, and that will verify the Eilenberg-Steenrod axioms, and then that will show that that will prove that the homotopy groups of the free abelian group are the same thing as homology. Okay. So, the three types of maps we're talking about today are covering spaces, fiber bundles, and fibrations. Too many typos. Yeah, so a covering space is a map where the fiber is discrete, some discrete set that does not depend on what point you pick in the base. These, fiber bundle is like a covering space, but the fibers don't need to be discrete. So the fibers, so if you look at the fiber by fiber, I just mean the preimage of a point. So the preimage of points in the base, and on which point you pick up to homeomorphism, and they glue together compatibly. There's some tapping somewhere. I don't know if someone's not muted.
Hunter, your microphone is on, I think.
Okay, great. And then a fibration is a generalization of a fiber bundle, and now the fibers can change, but they don't change up to homotopy. Yeah, so like up to homeomorphism, the fibers can be different, but up to homotopy, all the fibers are the same. And this is not almost definitions, but this is a heuristic for what you should think these types of maps are. Okay, so a map is a covering space if for each point in the base there's an open set containing that point, such that the preimage of the open set is just a bunch of copies of that open set. So here, like F is going to be a set that's in bijection with a preimage of any point, and then if you take a preimage of a neighborhood, you take a preimage of a sufficiently small neighborhood around a point, then it looks like just a bunch of copies of the fiber at one point cross the base. So here, this is B, and then this spiral thing is E. And this hopefully is a picture that everyone has seen when they took when they first learned about the fundamental group. Yeah, and then up here is U cross F. This disagrees slightly with the definition of a covering space, but when B is connected, this agrees with all possible definitions. Because I guess in some definitions, if B is disconnected, the fibers over different connected components are allowed to be different. Okay. So the picture of the spiral is the map from R to R mod Z, where this mod means like as a group. So Z is a subgroup of R, and the quotient is S1, and this is a fiber bundle with fiber Z. So maybe some terminology. The cardinality of the fiber is the number of sheets. So this is an infinite sheeted cover. Finite sheeted cover, one example would be the standard map from SN to RPN that sends, like a unit length vector to its span, to the line it spans. That's is a covering space map with fiber cardinality 2, so it's a 2-sheeted cover. Any questions? Okay, so another slightly more exotic example that will play a larger role in the course later. So the ordered configuration space of points in a space X is the subsets of, or the ordered configuration space of endpoints in X is the subset of X to the N of tuples where all the entries in the tuple are distinct. So I'm going to picture, this is a picture of an element of ordered configurations of 5 points in the cylinder. And then, this space has a natural action of the symmetric group by permuting the order. And the unordered configuration space is the quotient. So this is the configuration space of indistinguishable points. And there's a, map. The quotient space, I guess topologize everything with the subspace topology and then the quotient topology. And this is an example of a covering space with fibers isomorphic to the symmetric group. Okay, any questions? Okay, so a fiber bundle is like a covering space, but now the fiber doesn't need to be discrete. The fiber can have topology. So if we were in person, I would bring in a sheet of paper and fold it into a Mobius band and staple it together. Nobody seems to appreciate that, so probably it's good that some of you don't have to witness me making a Mobius band in class. Okay, so what's the actual definition? So a map is called a fiber bundle if there's an open cover of the base, and such that the preimage of this open cover looks like products. So there's open cover U alpha. Maybe I should have written brackets around U alpha. So for each alpha, if you look at the preimage of U alpha, that's going to be homeomorphic to the product. So locally, E looks like a neighborhood in B cross some fixed fiber F. And moreover, we can choose this homeomorphism to be compatible with the projection. So the product has a natural projection down to U alpha, and the preimage has the restriction of P, and we insist that the diagram commutes. Any questions?
So, trying to compare this back to the previous definition, the thing that we changed was that the fiber is not discrete anymore.
Yeah.
And then, so if we tried to apply this commutative diagram to the previous one, we'd just get something trivial because our fiber is discrete. Is that right?
Yeah. I think we don't need to impose. Somehow because the fiber is discrete, we got this for free, basically.
Okay. So the
And I
only
guess,
thing we really changed was that we said it didn't have to be discrete.
yeah. So if you plug in f is discrete, this is like a slightly inefficient way of defining covering space.
Okay.
Yeah, and I guess like because I whatever didn't think about it ahead of time, like there's no reason why I should have changed like for all B there's a U versus there's an open cover. Those are the same thing. Saying for all points there's an open set containing it is the same thing as there exists an open cover. And I rephrased that for no reason. Hopefully that doesn't cause too much confusion. I think I just like looked up the definition of a fiber bundle and looked up a definition of a fibration to make sure I was getting it right. I mean, covering space, and found them in 2 different sources. But yeah, sorry. Okay. Any other questions? Okay, so examples. So the 2 sort of trivialist, or the 2 least interesting examples. So covering spaces are fiber bundles. Great. So that's nothing new. And then the products are fiber bundles. So a fiber bundle is a map that's locally a product. Well, if it's globally a product, then it's locally a product. But the interesting examples, like y would somehow twist as you move around x. But if it's globally a product, then it is still a fiber bundle. Still a fiber bundle. Okay, so some less trivial examples. So the Hopf fibration. So you view S3 as unit length vectors in R4, which we can view as C squared, and then we can view S2 as CP1, which is the set of complex lines in C, and then there's a map from S3 to S2 where you send a element of S3 viewed as a unit length vector in C squared to the line it spans, viewing S2 as the set of complex lines in C squared. And this is a fiber bundle. And what are I claim the fibers S1. Well, what given a point in S2, so view that as a line in C, we're asking how many unit length vectors span that line. And so here we're viewing S1 as, so the fiber is S1 viewed as the set of unit length vectors in a line, in a complex line. Any questions? Okay. Oh yeah, so the next example is the tangent bundle of a sphere. So just view the sphere as is unit length vectors in Rn plus 1. And then the tangent bundle is the set of points in the sphere and vectors in Rn plus 1 such that the vector in the sphere is orthogonal. The point M in the sphere is orthogonal to the vector V. So here, I guess we can view the vectors as being based at M instead of based at the origin. And then, this is a picture of elements in, so I guess some terminology. If you have a fiber bundle, E is called the total space and B is called the base space. And F is called the fiber. So here's a picture of some points in the total space. This blue line and this green line are in the same fiber. They both map to, map to this point in the base. So the projection map is just forget the vector coordinate. And the fiber over a point is just homeomorphic to Rn. It's the set of lines that are orthogonal set of points in Rn plus 1 that are orthogonal to a given non-zero vector, and that's going to be a hyperplane, so that's going to be a Rn. Yeah, any questions? Okay, so the next thing is the tangent bundle in general, and yeah, so if you have a smooth manifold, what does it mean to have a smooth manifold? It means that there's some set and maps from Rn into your manifold, that are open embeddings, such that the images of these Rns cover your manifold, and that the condition of being smooth means that if their images overlap, you can get a map from Rn and then take the inverse map, and you get, I guess it's not defined on all of Rn, but it's defined on some open subset of Rn to some other open subset of Rn. The fact that M is smooth means we can pick these F alphas such that these compositions are always smooth. So that's what a smooth manifold is, and in fact, like a equivalence class of these is a smooth structure on M. Some manifolds don't have any smooth structure, and some manifolds have several that aren't equivalent. Yeah, so the tangent bundle is so we locally want it to look like Rn cross Rn, and what we do is so let me annotate. So now if I crossed off this part and I crossed off this, you should just get M. I guess, Silvio's, you're the only person who said that they have not seen manifolds that much. That if I cross off all the red stuff, does it make sense that this gives you M back?
Can you say that again a little bit slower?
Okay, so I'm saying I wrote down some formula, but then I crossed off a large portion of it. My question is, does the formula that M is this make sense?
Not immediately, no.
So, okay, so, S is the indexing set for our open cover. So what I'm saying is take, and the open cover is by sets that are homeomorphic to Rn. So what I'm saying is take S cross Rn. That's going to have a surjective map to M. Right? Like, if you have an open cover, you can take the sets in your open cover, disjoint, you can take if you have an open cover of a space, you can take the disjoint union of all of the sets in your open cover. And that won't be homeomorphic to your space, but it will have a natural surjection to your space.
So is S the open cover, or is it an index set?
S is the indexing set for the. Well, okay,
but S cross Rn is all of the sets in our open cover, at least up to homeomorphism.
Yeah.
Okay.
Yeah. And so then I'm saying, what are we double counting? Well, we're double counting if there's things in the intersection. So if M is in the image of I guess here M is in Rn, but you're thinking of M as in U alpha, that's going to be identified with this point, with the point that this corresponds to in the, so maybe we'll just say let U alpha be F alpha of Rn. Yeah, so what this is supposed to do is if you have a point in two different U alphas, you are gluing them together, or sorry, if you have a point in U alpha and in U beta, you just say, hey, that point, if you have a point in U alpha and a point in U beta or if you have a point in Rn. Okay, let me attempt to say this again. If you have a point in Rn, such that F alpha maps it to the same point. Let's call this point N. So here N and M are both being mapped to the same thing in the manifold. So like F. Let's annotate as okay, so what I'm saying is I'm saying that F alpha of M should be the same thing as F beta of N, unless I wrote the order wrong. I think the inverse I wrote incorrectly. Yeah, so N and M both map to the same point in the manifold. So we sort of want to identify them. So this equivalence relation, if you ignore the third factor, is just saying we're identifying points that, in the disjoint union of the open cover of the sets in the open cover that map to the same point.
Okay, yeah, that makes a lot more sense.
Okay, yeah. Ignoring this typo that I put the inverse on the wrong side. And then maybe I'll unannotate. And then ignoring that I put the inverse on the wrong side, what I'm saying is the tangent bundle of Rn is supposed to just be Rn cross Rn. So we're gluing, so we add this extra Rn factor. And now instead of gluing it using the functions, we use their derivatives. So it's like, so somehow, like this arrow, we are, could be viewed as an element of the alpha Rn cross Rn or the beta Rn cross Rn. And what we're saying is we're use the derivatives of the functions to this is also a typo because derivative here, I'm assuming derivative doesn't make sense except for maps from Rn to Rn. So I should have, this whole thing should be like d of f beta inverse f alpha. Because this is a map from Rn to Rn, so we know what taking the derivative means. Yeah, so I mean, maybe it's not important right now to fully understand this, but I'm just saying like it's something where you locally are gluing in a copy of Rn to each point in the manifold, and in the case of the sphere, or somehow I don't know. If your manifold is embedded in Rn, the tangent bundle you can think of as being the copy of, or if your manifold is embedded in Rm with M big, and your manifold is an N manifold, you can think of the tangent bundle as being like an n-dimensional plane tangent to each point. Okay. I'm gonna move on unless there are other questions. Okay, so the idea is we're going to I guess, to talk about this lifting property of covering spaces, observe that it also holds for fiber bundles, and then our definition of fibration is basically just going to be something with a lifting property. Okay, so some theorem like this, certainly when x is a point or an interval, this was covered in like when I taught point set topology. So it says that if the map P from E to B is a covering space map, and you pick an F from a space or CW complex X cross an interval into B, and you pick a map from X into E, then there is a map F tilde making the diagram commute. So here the map X from X cross 0, 1 is just, let's say, the inclusion into X cross 0. Okay, so maybe we'll revisit this diagram, but let me attempt to explain it in the case X is a point with a picture. Or ask people. Okay, so yeah, so let's say X is a point. So then, and then we're taking the map, the covering map R goes to S1. So viewing S1 as R mod Z. And so we're given F and F0 making this diagram commute, and then the claim is that we can find a unique F tilde making the full diagram commute. So yeah, we're given F0 and F making the diagram commute without this diagonal arrow, and then the claim is we can find a diagonal arrow. Okay, so any takers for like qualitatively, how should we think of F? F, I think, is okay, so maybe I'll just, probably the first question is too easy, so people are scared. So I'm just saying view F is just a path in S1. What is, so F is like some loop in this black circle. Not loop, some path in this black circle downstairs. What is F0 tilde? So, a map from a point, or, a map from a set with one element into a space is just an element of that space. So we have a loop down here, and then F tilde is some point in the space, but like what compatibility condition? What does the diagram commute mean about like what this point in R has to do with this point in, or this path down here? Also, yeah. Okay. I don't know if, okay. Zach answered in chat. Zach, can your internet is no longer terrible right now that you moved to Indiana. So you can talk.
No, I'm still in New York.
You're still in New York. Oh, so
Yeah.
it sounds better than it was like a month ago. Whatever.
Oh, okay.
Okay, so is it at least one per, but feel free to talk instead of chatting. Yeah. So okay. So what this is
Right.
so F is a path. F tilde is a lift of the start of the path to a point upstairs. Sorry, F tilde 0. F tilde 0 is like a choice of this point. Yeah, so this is picking this point as f0 tilde. So, we could have picked some other point that also mapped. So down here, like this is where f of 0 is that point. And what we need to do is we need to pick a point in R in the spiral that maps down to the start of the path. And then the claim is that, and then f tilde is just a path upstairs that maps to our chosen path downstairs. So unique path lifting says that given a lift of the start of the path, we get a unique lift of the rest of the path. You're sort of, this path goes around like that, you're forced to go around like that. Anyone want to I will move on, or if two people say they're happy before one person says they're confused, we should wait 10 seconds for someone to say they're confused.
Can you go back to the previous slide? I didn't get a copy of the general diagram down fully.
Oh yeah. Oh yeah. Yeah. So this is the general statement. So yeah. So I plugged in x as the point. So it's like path lifting but parameterized by x. So I think in I don't know, when I taught this, I think I just did the case that x is a point and x is an interval, because you sort of want to lift paths and then you want to lift homotopies between paths, but x can be basically anything. I think x just needs to be like locally, I don't know, path connected or something. Forget what the actual point set topological assumptions on x are, but CW complex is sufficient. Yeah, so it's saying that if you have a path in B and you lift the beginning of the path, you get a unique lift of that path to E. Moreover, you can do this compatibly in like families of paths. If you have families, a family of paths parameterized by x in B, and a lift of a lift of the start of the path of each of the paths to E, you can uniquely extend it to a family of paths in E. Okay. Yeah. And these are not my best paint pictures. Okay. What was I saying? So, so the theorem is for fiber bundles, we have the same statement, except unique has been dropped. And I guess instead of writing out a commutative diagram, I wrote out what like equalities of function composition should be true. Yeah, but so if you have a fiber bundle, the same thing is true, except it's no longer unique. So yeah, so like let's say E is just product bundle. E is the interval across the interval, and B is an interval, and the projection map is just oh yeah, and this is a typo. Not really a typo. Oh yeah, and then let's just take no, this is a typo. B is an interval. I think B 1. Oh yeah, and we'll take capital X be a point. Sorry for all these typos. Yeah. Actually, let me just pull up the next slide. Okay, yeah. So this picture is supposed to illustrate non-uniqueness. Let me go back and fix all of the typos now. Typo, I want x to be a point, not an interval. And then this is a map from the interval to b. Okay, yeah, so the claim is that in, and let's say we lift, yeah, so let's say that our path in b is, b is an interval, our path is just, the identity map from an interval to itself. And let's say our lift f tilde lifts the left endpoint to 0. Well, what are choices of, f0 tilde is just the lift to 0. I'm saying f tilde is, the data of f tilde is just a function from the interval to the interval such that 0 goes to 0. Yeah, so let me, yeah, so I guess, yeah, because what does it mean that, f equals p composed with f tilde? Well, in this case, f is the identity map from the interval to itself, and p is just projection. So this is the statement that f tilde, f tilde is a map from the interval into E. This equation, the fact that it's a lift of the identity map means that f tilde is just a function. And then the fact that f tilde extends f0 means that the value of the function on 0 is 0. So here it's clear that lifts exist, like functions exist, but it's also clear that it's not unique. There are lots of different functions from the interval to the interval, whose value on 0 is 0. Anyone want me to say something again? So, upshot is, so I mean, the theorem says that we have lifting, we just don't have unique lifting. And so sort of like why we have unique lifting in the covering space case is like the blue line and the red line, if the fiber is discrete, somehow like can't separate from each other. But here the blue and the red are doing the same thing in the sort of base direction, but they're moving in the fiber direction, which they can do because the fiber has topology. I don't know if that's helpful. Or is there anything I should repeat? Okay. So the definition of a fibration is just going to be something that has lifting. Which initially seems odd. So a function is called or continuous function is called a steric fibration if if it has this lifting property. Yeah, I feel like I should have it. If we were in a classroom, I would have written on a sideboard the diagram giving a fibration. Oh yeah, so I mean, everyone knows like notes are on my website, and like everything is recorded on YouTube, hopefully. Okay, so what's an example of a fibration that isn't a fiber bundle? Well, you could take E to be this solid triangle instead of a solid rectangle mapping down to an interval. And now, you have some path downstairs, we can lift it to a path upstairs, and it, not necessarily uniquely. And, question like, why is the projection from a triangle to an interval not a fiber bundle? Zach should answer this in like a minute if no one else answers it. Yeah, so like I'm claiming this is an example of a fibration that isn't a fiber bundle. So why is this not a fiber bundle?
Because like at one point, or
I
at
think
the
two
end,
people are
you have
talking.
the fiber is just a point where it's like.
Yeah. So a property
Oh, sorry.
fiber bundle is that the preimage of each point, there's this fixed space F, such that the preimage of each point is homeomorphic to it. And here, if you take the preimage of everything but the rightmost endpoint, the fiber is going to be homeomorphic to an interval, but the fiber over the right endpoint is just a point. So it's definitely not a fiber bundle, but you can still lift, using similar pictures to this. Yeah. Okay. Yang, I think you started talking slightly before Zach, so you should just be rude and tell him to stop talking. Okay. What are we doing? So another example that's is the path space. So remember I is my shorthand for an interval, which I sometimes use, I sometimes don't use. So it's just the space of based maps from an interval into X. And so we'll pick the base point in the interval to be 0. And there's a map there's an evaluation map from the path space into X where we just evaluate if F is a path, P of F is F of 1, so that takes a path and outputs a point in X. Yeah, so on Tuesday we had a name, or what is the preimage of the base point in X? So on Tuesday we gave this space a name. So it's a path in X, and 0 goes to X naught, and then being in P inverse of X naught means 1 also goes to X naught. So this is exactly just the loop space, the based loop space. So it's maps from the interval that send both 0 and 1 to X naught. Yeah, so do the fibers depend on X? If I was like better at doing this, I'd be like, okay, let's vote or something. Type in chat. Oh, okay. Yeah, so the fibers do depend on X. What are the fibers? The fibers are paths that start at X naught and end at a point X. So in general, this could the homeomorphism type of those mapping spaces could depend on what X is, but they don't depend on X up to homotopy, because there are maps where you concatenate. Oh, let's assume X is connected. This is why is this wrong if X is not connected? Like what's the fiber over a point? What's the fiber? What is P inverse of X if X and X naught are not in the same path component? What are the sets of paths from two different points that are, or from 2 points that are in different path components? No one wants to.
I mean, it's the empty set.
The empty set, yeah. So yeah, so if X is not connected, then this is whatchamacallit. Yeah, if X is not connected, then or not path connected, then if you pick a point in a different path component, you'll get the empty set. But if you pick a point in the same path component, you'll get something that's non-empty, because by definition of being in the same path component. But if X is path connected, then the fibers don't depend on what point on X up to homotopy. And the way you'd prove that is you would you'd pick a path between the points that by concatenating with that path, you get a map between the fibers, and by concatenating with a path going the opposite way, you get a not a strict inverse, but an inverse up to homotopy. So this is similar to the proof that the fundamental group doesn't depend on base point for path connected spaces. Okay. Yeah. So there's a theorem that says E to B is a fibration, and you pick a path in the base, and you name the two endpoints of the path B0 and B1, then you get a natural isomorphism between the homotopy groups of the fibers. And the way you prove this is you just sort of pick a you use path lifting, some clever choice. So a corollary of this is if B is path connected and all the fibers are CW complexes, then the homotopy type doesn't depend on B, on point B in the base. So this corollary, the way you prove the corollary is just you use Whitehead's theorem that says if you have an isomorphism on homotopy groups, then you get or if you have a map that induces an isomorphism on homotopy groups, then the map's a homotopy equivalence. Okay. Yeah. So maybe what you should think of is, if you're a geometric person, then you might think of like, oh, if I have a path, and like sometimes I can do like parallel transport and compare fibers using a path. And here, it's saying like up to homotopy, there's like a well-defined parallel transport. Okay. So the reason why we're interested in fibrations in the beginning is because they give a long exact sequence in homotopy groups. Yeah. So if E is a point in the total space E, E0 is a point in E, then we'll let B0 just be the projection of E, and we'll let F be the preimage of B naught. So in particular, E naught is in F. So then the statement is you get a long exact sequence of homotopy groups, and this is exactly what we would need to prove the long exact sequence of a pair in the if we can show that the map on free abelian groups is a fibration. There's a warning that I'm not going to care is needed when I is equal to 1, because pi 0 is not a group, so you might not know what long exact sequence means. And so, if it looks like the theorem is true in the way you're applying it, then you can apply it for pi 0. But if it looks like it's not true, then you're not applying it correctly, is all I'm going to say. Yeah. Okay. So I'm not going to prove this theorem, but the hardest part is figuring out what this map is. So I'm going to try to tell you what this map is. What the connecting homomorphism is. Yeah, so the other maps, the map from here to here is just, F, there's a map of spaces from F to E. You get an induced map on homotopy groups. What's the map from here to here? There's a map of spaces. You get an induced map on homotopy groups. So the only thing exotic is this map. Is this map doesn't you actually can make this come from a map of spaces if you use loop spaces, but I'm not going to do that. So I'm going to I'm going to tell you how to construct this map, and then checking exactness is not that hard. So maybe for example, part of exactness means if you have an element here, you map to 0 here. Well, why is that? Well, the entire fiber maps to B naught. So if you have some sphere here, it's going to map literally to the constant there. So that's part of exactness. The other parts are probably slightly harder, but not much harder. But yeah, but the main idea is how do we build this connecting homomorphism? And that's going to use that it's a fibration. These maps exist, if you have any space E and a map to B, you can always look at the fiber over E, and you can look at the map to B. Okay. So now we're trying to describe the connecting homomorphism. So, we want an element. We want an element here. So you can think of an element in pi I plus 1b as this map of pairs from interval to n plus 1, rel boundary, into the pair b rel base point. Yeah, so you have a map that's going to give you an element in the homotopy group. And at the end of the day, we want an element here. So hopefully this is an element in pi I f. We want at the end of the day. Okay. Yeah, so what's the first step is, well, we need to use that this map P is a fibration. So let me just redraw the diagram. So the diagram says that if we have a map x cross I into B and x here, then we get a map like that. So how do we get a map from x cross I into B? Well, we'll just let x be I to the n. I to the n cross I is I to the n plus 1. Great, so we're just going to view F as a map from x cross I into B. Now we have F, and then we want an F0 twiddle. So the next observation is that, okay, so F restricted to x cross 0 is constant at B0. So why is that? Well, x cross 0 is a subset of the boundary, right? Like if n is 1, then I to the n plus 1 is a square. So that's the boundary of the square, and then this green is x cross 0. So the entire boundary goes to the base point. So in particular, the left part of the boundary goes to the base point. So because the green, because x cross 0 goes to the base point, we can define f tilde to just map to the base point in E, because the base point in E maps to the base point in B. So now we have our left f tilde. This is a constant map. Okay. Any questions up through like observation 5? Okay. So now let's see. I think this Jn is going to be the other part of the square. It's going to intersect the green part at the points, but so Jn is like the closure of the boundary minus x cross 0. What you should think of Jn. So x cross 0 is the left part of the square. Jn is the right part and the bottom and the top. So, the observation is that Jn is homeomorphic to In. Like three sides of a square is homeomorphic to one side of a square. Or, it's homeomorphic to an interval. So what we're going to do is we're going to okay, so what are we going to do? Well, we're going to pick this lift f here that goes from x cross I into E, and then we're just going to restrict f to Jn, but then identify Jn with In. So f restricted to Jn gives us a map to E, and we're just going to say, okay, I'm going to view Jn as In. So it should be clear at this point that this is a element here. Oh yeah, so someone should be confused, probably.
I don't see that last part you said.
You don't see.
It should be clear that it is an element of pi I. How so?
Oh, okay. So, sorry, this is f tilde. You agree f tilde is a map to E?
Yes. Yeah.
Yeah. So then we're, f tilde is a map from In plus 1 into E. And what we want is we want a map from In into E. So, like in the picture, we have a map from a square into E, and we want a map from an interval into E. And so the interval we're picking is this, Jn.
Right. Yeah. Okay. So that's why you said the whole thing about the three sides of the square being an In.
Yeah.
So that we do get a map from In into E.
Yeah.
And you're claiming that that is an element of pi I E.
Yeah. We really want it to be an element of pi I f, but I'm saying it's easier to first see that it's an element of pi I e.
Okay.
And then, so, you know, the question, okay, how do we know it's not just a path in E? Like, you know, in the picture, this should be an element of the fundamental group, not just a random path. Well, the base points, running out of good colors, the base points are, this is going to be black. What are my colors? I don't know where to pick. Okay, purple. Know how to draw. Don't know what I'm doing. Okay. Those purple points, because I can't find the normal drawing tool, those purple points are in X, or X cross 0. And so our chosen lift, our chosen F tilde sent everything to E naught. So the purple points go to the base point in E. So that tells us that that this element is not just a random, that when you restrict to Jn, it's not just a random path in E, but is in fact a path that sends the boundary to the base point. So in the n equals 1 case, it would be an element of the fundamental group instead of just a random path. And then so yeah, so I claim that I've said enough to see why this construction gives us an element of pi I of E. Any questions on that before I explain why it actually lives in pi I of F?
Yeah, so just to be clear, with that remark about those purple points being glued together, what you mean is that you actually get a map from a circle, right? To that sort of path, a closed.
Yeah, I guess I was viewing the fundamental group as like maps from an interval that send both endpoints to the same point.
Okay, yeah, that was what was kind of confusing to me because since
Yeah, I mean you can either here I'm viewing homotopy groups as we send like a cube, maps from a cube that send the boundary to a point, but you could also just say that's the same thing as maps from a sphere.
yeah, exactly. I was
Point to point.
thinking of
But I think it's slightly easier with cube's rel boundary here.
Yeah. No, but I see it now. It makes sense.
Yeah. And so in general, F tilde will send like all of the square. You know, there's no reason for F tilde in general to map to F. But F tilde is a lift of F. And F sends the entire boundary to B naught. So that means F tilde needs to send the boundary to parts of E that map to B naught. But that by definition is F. So the fact that this diagram commutes and that F sends the boundary to B, and the fact that Jn is a subset of the boundary means that F tilde restricted to Jn is going to, you know, needs to map to points, you know, F tilde, if you need to find this pen. Okay. Yeah. So if you start out in Jn and then take F tilde to E and then map down this composition, make my picture terrible. This composition ends up just at B naught, which means that you know, that if you just start out here, go here, and go here, you're going to end up in the preimage of B naught, which is what we're calling F. So that's why this is an element in pi I of F, not just an element of pi pi I of E. Yeah, so in general, F tilde sends things into parts of E that aren't F, but it'll send the boundary into F. Anything I should repeat? Okay, great. I think this is the important part. Now I'm going to just rush through applications quickly. Oh yeah, this picture, I was thinking, yeah, this picture is basically what I said before. Okay, so the now that we have this long exact sequence, let's get some corollaries. So the claim is that if you have a covering space, then the covering space map will induce an isomorphism on higher homotopy groups. So certainly need not be an isomorphism on fundamental group. Like if E is the universal cover, the fundamental group will be trivial of E and won't be trivial for B. But higher homotopy groups will be an isomorphism. And how do you see that? Well, you just look at the long exact sequence. So because the map's a covering space, the fiber is discrete. So that means all the homotopy groups starting at 1 will vanish. So, pi IF is 0 and pi I minus 1 of F is 0, assuming I is at least 2. So that'll make the middle map an iso. Proof. So in particular, the higher homotopy groups of S1 are trivial because the higher homotopy groups of S1 will agree with the homotopy groups. Will agree with the homotopy groups of R, and R is contractible. So okay, so we've computed some higher homotopy groups of spheres. Let's do a slightly less trivial example. So let's prove Hoff's theorem that pi 3 of S2 is Z. So so if you look at the long exact sequence, we get pi 2 of S1, which we just said was 0. Over here, pi 3 of S1, which we said is 0. And then we get pi 3 of S2 maps to pi 3 of S3 mapping to pi 3 of S2. So so this proves that this map is an iso, and then pi 3 of S3 is Z by the Hurevich theorem that says that if in this case, if the first two homotopy groups, or if you have a simply connected space and the first two homology groups vanish, then the first two homotopy groups will vanish, and in degree 3, homology will equal homotopy. So this equality follows from Hurevich. And so then you get that pi 3 of S3 is 0 because of long exact sequence. Oh yeah, I finished early. Oh yeah, all these slides, there's homework. Nobody's doing the homework, but I'll still probably.
I have a question here. On this last slide. So on this sequence, what is the B, the E, and
Oh yeah, sorry.
could you
Yeah, maybe I should have written that out.
write
So
the
the
square?
Hoff vibration from earlier was saying that there's a good color 3. That there's a fiber bundle like this. So that's saying that this. Better colors. I don't know what just happened. Sorry. Hopefully you can hear me. I don't know why I don't have the annotate slide.
Yeah, I can hear you.
We can hear you.
Okay. Yeah. So S1 is the fiber. S1 is F. S3 is E. S2 is B. Okay. Technical. Yeah. So this is E. E F, and then this map is delta. So this is the one that lowers homotopy groups, and it goes to, from the base to the fiber. And this is the Hoff fibration. So here we're thinking of S3 as unit length complex vectors in C squared. We're thinking of S2 as lines in C squared, and we're thinking of S1 as unit length vectors in a fixed line. Yeah. So yeah, but there's no this Hoff fibration is kind of a special thing that doesn't really generalize that well. So you sort of can't use this strategy to compute like pi 4 of S3. Yeah. Any other questions?